Hello and welcome to the bare metal programming series where we're building firmware for a Cortex-M STM32 microcontroller. Now this is episode 7.3, let's call it, and this is kind of the third part in our packet communications protocol build. Now in the previous episode we actually built the packet protocol. So what that means is we define the data structure and we built out a state machine, a module that kind of contains a state machine which is able to convert our kind of incoming UART byte stream of received bytes and turn those into packets. And those packets are, they become reliable. So the UART stream can be, it can pick up interference, and the packets have a CRC built into them. And that CRC is checked when a packet is received, and if the packet doesn't actually check in terms of the CRC, then we automatically request that the sender send that packet again. And otherwise we automatically acknowledge that packet, letting the other side of the communication know that they're free to send the next thing. So that's what we did in the previous episode, but we didn't actually test it. Because that would have taken far too long. So that's what we're going to be doing today. And let's not waste any kind of time. Let's go straight into the plan and see what we're actually going to be doing. Alright, so 7.3. The goal of today is to get confidence that the packet protocol is working as intended. That sounds about right. We need to fix the bugs. So I've already been through this, of course, and what I figured out is that there is at least one bug in this implementation. Kudos to you if you spotted the bug. It's a great one. But that particular bug that I found, and we may find more during this, but the particular one that I found is a great example of, it allows for a great example of a cool debugging technique that if you happen to use Visual Studio Code, that you can employ in your development debug lifecycle. And it's actually a debugging technique that can be used in almost every programming language that has a good integration with the VS Code debugger. So I think that's really worth looking at. Before we get into the bugs or anything like that, I want to show the client-side firmware update program that I've written. And I've put it in quotes here because it doesn't do any firmware update or anything like that at the moment. It's very much a bare bones, minimal amount of code to get up to the same communications protocols we have on the firmware. So it's written in TypeScript. We could have done this in any language. I actually did try to write this in Python at first, and I had some issues with the serial port library there. So I wrote this one in TypeScript instead, and it uses a single dependency, which is the serial port library, and we implement the same packet protocol as the firmware. So the first thing I want to do is to just take a look at that code. So as you can see here, here's our one dependency, and here is the file in question. So I've commented all the code and everything, so you can take a look through it, but it's just a one-pager. It contains everything we need in this one file. Of course, when we build the firmware update tool, we might want to kind of clean this up a little bit as well and move things around and, give things a home. But so far, this is what it looks like. So in the beginning, we've got a bunch of constants. These come straight from the firmware, just what we wrote in the bootloader. So we've got our packet kind of length and definition and all of that kind of stuff. We've got our two special packets, two special bytes that convey packet meaning. Then we have a little bit of information that describes our serial port. So this is just where we can find our serial port. This may differ depending on where you, on which platform you're on, and how it manifests depending on which kind of chip you have, baud rate. Then we have a CRC function, so this is just the same CRC function as the C implementation, and if you put them side by side, you can really tell that they basically are one-to-one. So I'll let you go through this and check them if you want, but it's just a one-to-one correspondence. Only in the TypeScript implementation, we have to do all of these and FF operations because, JavaScript and TypeScript, by definition, when you do bitwise operations, you don't stay confined to 8 bits. It actually will automatically convert the number into a signed 32-bit integer. So you always have to do this and FF operation to keep things within the 8-bit domain. Of course, we don't do that here because we just have an 8-bit type, and it has, in this implementation of C, for this microcontroller, it has overflow back to 0. Okay, so that's the CRC, nothing special there. We got a little delay function, so this is just a promisified version of the set timeout. I've used this a lot of times, and any time that you've wanted to have await some amount of delay, you've probably written this function yourself as well. Next, and probably kind of like one of the most important parts of this, is that we have a class for packets. So this just is kind of like the structure plus a bunch of useful functions that we had in the comms.c. So this kind of combines those together. We have a length, a data, and a CRC field. The data field is a buffer, so that's a node buffer. It's basically like an array which is fixed for storing, like integer types, but has all kinds of functions and methods and everything to be able to write specific values in and different sizes and all that kind of stuff. It's very much like an array buffer with a data view, and I think it's even built on top of those these days. But that's what we have there in the data fields. A couple of static fields which are just packet instantiations of specific packets. So we have a retransmit packet and an ACK packet, just like we can do packet.retransmit and ACK, and then we can use those. And they're already buffers, as you can see right there. They're converted to their data representation straight away. The constructor is nothing special. Basically, you can pass just the length and the data. You don't have to pass the CRC. And if you don't pass the CRC, it will compute the CRC automatically. So that's quite useful if you're trying to construct a packet, like, hey, I want to send some data, here's my length, here's my data. You know, the constructor will figure out the CRC for you. If you're deserializing a packet, you can provide the CRC, and then you have a complete packet as was transmitted, but in the form of the data. And you can use the compute CRC function to check that against the packet you received. It automatically pads as well, so if you pass data that isn't the full 16 bytes of the packet, then it will automatically fill those other missing bytes in with FF. Compute CRC, nothing special, just does exactly what we do in the other one, which is just to compute a CRC based on the length and the data. We have a toBuffer function that basically converts all the packet that we have in this class back into a node buffer, which is just, you know, a concatenation of a buffer made from the length, the actual data, and a buffer made from the CRC. You have to concat buffer objects together. We've got this similar utility function, is single byte packet, so this is just the same implementation as we have in the C. And then again, two useful functions, is ACK and is RETX. We don't actually use those at the moment, I think. Or at least we don't use the... No, we do use those. Then we have the actual serial port object from Node, from the serial port library. The serial port library is built on a Node extension, so it uses native C++ in order to tap into the serial port stuff. I've used it a couple of times. It's quite a good library, and by default it's built on an event emitter. So we'll create an instance of the serial port. This will error out if it doesn't work. Then we have just some variables here for storing packets. So this is just where we're going to stuff the packets as they come in. We don't have to do any special ring buffer type stuff in TypeScript land, because we just have automatic garbage collection and extending arrays and all of that kind of stuff. So that's one of the nice things also about working on firmware for a while, is that when you come back to a high-level language, you can really appreciate the high-level data structures that it gives you, and the ease of use of not having to kind of think too much about the memory and the fact that you can't allocate and all of that kind of stuff. So just little thanks to TypeScript there. Thanks for having a nice, simple model for data. We can just stuff things into this array. Next up, we have a buffer just for the bytes that are coming in. So this is purely like the UART buffer, and this is the packet buffer. And then there's a little utility function that basically acts like splice. So we can like remove a section of the UART buffer, the RX buffer. We can just remove a section of it and give it to the user, and then that's gone from we can sort of consume it from our buffer. So that's what that function does. This is actually the state machine implementation, more or less, and it's a lot simpler in this respect. So what we actually do here is we add a bunch of data to our RX buffer. So however much comes in, it comes in on this data object. When the UART serial port, when we get data, we get a data parameter here, and it's just a node buffer. So we just concat whatever we had in the buffer previously with the new data. And then we just check, do we have enough data to build a packet? So that's another nice thing here that we don't have in the firmware. We actually know how much data we have in the packet, so we can actually say, hey, we don't need to, you know, as each byte comes in, stuff it into the right portion of the data structure. We can just wait till we have the full 18 bytes and then actually just use them all at once. So that's what happens if we have enough bytes to build a packet. We consume those bytes from the RX buffer using this function that I just talked about. That will actually give us a node buffer that has 18 bytes in it, and it's our kind of raw packet. Then we can actually build a packet from that. So we build a new packet, and the length is in the first byte. The data is in everything from the first, the 1th byte up until the second to last, and then finally the second to last byte there, we have the CRC. So then we actually can compute the CRC of this packet, and we can compare them. So if they don't match, we simply write this packet RETX, the retransmit packet, to the UART, and this is already a node buffer. So we're just sending some data out as a node buffer. And this is really the reason that we're using node buffers, is because the serial port library uses node buffers. So it's kind of the easiest way to interface with it without having to kind of translate the data. Normally in a lot of my videos that make use of kind of binary data in JavaScript or TypeScript, we've used the uint8 array most of the time. But yeah, there's no point in kind of using that and then kind of converting to a node buffer, and we may as well go all in on the node buffer. So if it needs to be retransmitted, we can just return at that point. We don't need to do anything further. We've just asked for a retransmission. If it's an acknowledgement packet, we also don't need to do anything, right? We've had whatever our last piece of data was transmitted, back to us. And actually, I'm realizing that we're missing one thing here, and that is we're missing the retransmit. So it's good that we did this. So I'm going to make a variable here, last packet, which will just be a packet, and we'll just set it to be a new packet of length 1 that just has FF by default. So it doesn't really have any data in it. And this should be a node buffer, so we need to do buffer.from and just treat that like an array. Alright, so like that's not a real piece of data that we actually want to retransmit, but we'll leave it like that. Actually, maybe we can just have like an acknowledgement packet as the last thing, so that will be even easier. Okay. It's declared, but we never use it, and that's a buffer. Oh, that's the problem with this, of course. I guess we could just have a buffer instead. There's no need to be able to go back and look at the last packet. So we'll store our last packet, and now we can actually check if are we being asked to retransmit. So if we are, that's basically something we can check this way. If packet is RETX, then we'll send back our lost packet. And since we're writing our lost packet, we don't need to store it at that point. that's it. We don't need to store anything further from that, and then we can move on from that. And finally, if we get to this point, then the packet is just a piece of data that we need to have, and we should actually stuff it into our buffer and acknowledge the packet that we had. And what I might actually do is to also create a quick function here, which will let's do it like this: send or write packet. We'll get a packet, which will be a buffer. Mixing terminology here, but it's all right. You are right, the packet, and we'll also set our last packet to be that packet. Okay, and then in these instances where we've used you are right, we'll just do it like this instead. And that will just ensure that whenever we send a packet out, that that we also store whatever our last packet was. Okay, so it's good that we go through this. And then finally at the end, this is kind of the actual program. So all of that is just kind of like, this is the state machine, we've got a data structure for the packet. Finally at the end, this is our real kind of program. And I've wrapped everything in an async function called main, just because. And what we do here is that we say we're going to wait for a packet. We call this wait for packet function. All this does is go into a while loop, checking that we have at least one packet, and we delay for a millisecond if we don't. And eventually, when we do have a packet, we just return. So you can see that we probably want to have some kind of timeout on this eventually. That will probably be a good idea. But for now, this is fine for the illustration purposes. So we're just going to wait here for packets to come in, and then we're going to log it out when it comes in. So that is how the the firmware update code looks. And of course, the actual firmware update communication, it will just go in here eventually. And that's what we'll write. Everything else will probably stay the same. Okay, so that was kind of the quick introduction to that. I didn't want to write all of that on camera because I just thought it's so similar to what we've already done that giving a rundown would be a better use of everyone's time. So next up, we need to actually set up the bootloader. So we only wrote the communications protocol before. We didn't actually kind of put it into practice in the bootloader. So that's going to be our first kind of our first port of call, so to speak. We're going to want to actually sort of have a bunch of stuff that happens before we jump to main. And I think in this example, we just won't even jump to main. We'll stay in the bootloader just while we're testing this stuff out. Okay, so what are we going to need? We're going to need our core. We're going to need a few things. We're going to need core UART. We're also going to need core system, because the system is going to give us the systick, right? If we set up the system, then we'll have systick, and we'll be able to wait for certain amounts of time, and that will be useful just for while we're doing some testing. And we're also going to want to have our comms. So we're going to bring that in, and we're going to set these things up. So we are going to set up the system first, system setup. We're going to do UART setup. We're going to do comms setup. And then at this point, everything is kind of good to go. And we'll have some kind of while true loop here that will act as our kind of main firmware thing. And we can already just put a system delay in here of, I don't know, 500 milliseconds for now. So this is going to form the basis of our program. Of course, we also need to set up the GPIO, right? Because this program doesn't initialize any of the pins or anything. So in order for us to actually speak UART, we need to configure those pins as GPIOs. So this is just going to basically be exactly what comes out of firmware here. So I'm even just going to copy some of these things for now. If we are actually going to share them, we can put them into a different place. But for now, I'll just copy this. We need to bring in GPIO. And we'll also need to bring in RCC, because we're going to need to enable the peripheral clocks as well. All right, so when we set up the serial port, we're going to grab this, and let's just make a function for GPIO setup. Okay, then we can call GPIO setup here. And we're also going to want it to configure the, does UART already configure the UART? Yeah, it already enables the clock. Okay, so we don't need to do anything further with that. We just need to enable the GPIO, and that should be good enough for that. Now, I've left it kind of at the end here, but you can already see, right, that there could be a problem here if we're doing all this kind of setup stuff and eventually we jump to main, but we never really reset the chip or anything like that. So there is kind of an issue here, and that is that we're doing, we're like configuring some GPIOs, we're like telling the peripheral clock to be enabled to this peripheral or this peripheral. You know, we've got it going to the UART, we've got it going to our GPIOs. We have interrupt handlers in the UART, we have interrupt handlers for the SysTick. And you can imagine, right, that if we eventually jump to our main program, those don't magically stop having been configured. So even in the main application, we will very quickly jump into, we could end up jumping into an interrupt handler back in the bootloader. But except that that wouldn't happen, because the first thing that we do in the firmware is to set the vector table offset register, which means that we would inadvertently jump to an interrupt handler that was defined somewhere else. Now, that may not be a problem, right, if we have just like a handler that's just configured to be kind of like a no operation, like just immediately jump back and return. But if we actually did have UART set up here in the bootloader and in the main application, well, the problem there is that if UART and the ring buffer and everything like that hasn't been properly configured in the main application, then we could get a byte that activates our interrupt handler, which assumes that we've already set up our ring buffer and everything and tries to write into uninitialized memory. And that may be okay, that may not be a problem, but it probably isn't going to work out like we want it to. So the big note that I'm trying to make here is that we're kind of going to need to address teardown at some point as well. And that teardown is basically going to have to happen symmetrically with this stuff before we jump to main. So that's just a good note to really put in here, that we're going to need to do some teardown. Probably not going to cover that today, but we'll do it when we get to the bootloader state machine implementation and all of that. It's definitely something that has to happen before we end up going back to the main. All right, how can we kind of, how can we do some testing on this? Well, we can first just kind of see what happens if we send a regular packet. Let's just see if this works out. And spoiler alert, it's not going to work out because there is a bug. But let's just see what happens when we do this. So let's create, first of all, a comms packet T. It's going to be our packet. And we can set this stuff up. So it's going to be of length 1. And the data inside is going to be, let's make it like 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we need, what's this? 7 bytes of FF. FF. Right, and then let's say we have 9 valid bytes. Why not? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Right. And the CRC, it doesn't need to be, we need to compute it, so we'll just set it to 0 here. We will compute that CRC, so we'll do comms compute CRC. We'll pass in our packet, and we need to assign the result of this to packet.crc. Alright, so now we have a packet, and we can just do uart write, or rather we should do comms write, and we should send our packet into that. So what this program is going to do is set everything up, create a packet which doesn't have any special meaning or anything, but should be a valid packet, and we're going to send it, and that's it. And then kind of in our in this program we're going to run, we're just going to sit and wait for a packet to come in, and then we're going to log the contents of that packet. So let's try that. But of course, for that to take place, let's also just put a little bit of instrumentation here into this UART thing, so we can see when data has arrived. So console, let's say received data.length bytes through UART, and then we can say that we are building a packet, and if we fail CRC, we can say that CRC failed, expected, and the expected value of this is the packet CRC. But we got, then this will just be our computed CRC. Actually, I guess this is the other way around, isn't it? What we actually expect is the packet CRC, but what we got is the computer CRC. It's kind of difficult to phrase this in terms of the expected. I get it depends on what you what your perspective is here. Do you trust the packet or do you trust the thing? But let's just call it computed CRC, computed blah blah blah. But we got this one. All right, good enough. If it was a retransmit, let's just say that retransmitting lost packet. And it was an ACK, nothing to do. Storing packet and ACKing. Okay, so now we've got a bit of instrumentation in there as well, so we'll be able to kind of see what happens as as data moves through that quote-unquote state machine that we have here. So I'm going to run the program already. TS node. Wait, are we sending anything in the firmware? We are only sending if we send something, so no. So we shouldn't expect that there are bytes coming across the serial port. All right, so TS node firmware updater, and you can see, oh, that's not what I expected. So there's a whole bunch of data apparently coming through at this point, which is strange. Let me that's really strange. So in the firmware, I'm not sure exactly what firmware image is on there now, because of course I've been testing. So what I will do is I will first run the debugger in the bootloader. And of course we need to update the make file as always, so we're missing the system. That should be everything. So let's make yeah. Okay, so I'm going to run the bootloader in debug mode. So here we are, and now we can actually run the program, and we can be fairly certain that there shouldn't be any UART traffic. Alright, we're waiting for a packet. Nothing's happening. Let's jump down to here. So we're going to, here's our packet. here's the data, and here is the CRC that gets computed for that, so 175, and then we're going to write that packet. We're going to write that packet to the UART. So I guess I will put a breakpoint here, and then here we got 18 bytes through UART. We built a packet, but the CRC failed. We computed 52, but we actually got AF. And I think if we look at here, packet.crc, we look at the thing, we actually did send AF. So it's not a corruption. There is, for whatever reason, a difference in the CRCs. So I just want to show you, I've actually fixed this bug already. And I just want to show you like how I solved it, and a nice little tool for solving it using the debugger. So whenever something goes wrong with CRCs and they don't check out, it can feel a little bit like a brick wall, like, well, okay, there's just two different values. Why? One's being sent, the other is not. So what I like to do is I just like to put a log down of which byte came in and what was the kind of resulting CRC. I think that is a useful way of tackling this. So this. Okay, so what I'm going to put down here is that the byte that came in is data at, well, it's this byte variable. So it's going to be byte.toString 16. And what doesn't it like here? Can't find name byte. Because we are out of the loop. True. And the resulting operation from the resulting value from this is just CRC. So let's just put these two values down. We'll log them out, and I'm going to do the same thing in the firmware. But of course, we don't have a console in the firmware, right? That's we do. We have a UART, but what we're trying to test is the UART. So it's kind of what we're trying to test involves the UART. Let's say. So it's kind of a difficult thing, right? We're sort of mixing all these things together. We can't really log the UART out because we need to run this program, which needs to be connected to the UART in order to see it. So we're kind of at an impasse there. But luckily, there's a really cool feature which I don't think too many people actually know about. I certainly didn't know about it until a little while ago. And it's something called log points. And it's kind of a variation on a breakpoint. And you may have seen me use conditional breakpoints in the past. And that's when we kind of like, maybe we only want to break on this if certain conditions true. So maybe we would only break on this line if the packet CRC was equal to AF. Right, and then like if we actually ran this now, and we let it run, well, apparently we didn't break at that point, so that's kind of an issue. But that's weird. What is packet should be AF, but I'm really not sure my. Well, that's kind of weird. Anyway, that's not what I'm trying to. That's not what I'm trying to show you at the moment. But that I felt like that should have worked. In any case, what we want to do is we want to go to the CRC implementation in the C code as well, and to basically put the same log down and just compare the two and see what's actually happening. So to do this, the tricky thing is I actually want to put a log at this point. So I'll show you where you could put a log. So here we can put a breakpoint, right? And you can only do this on lines that you could put a breakpoint on. So if a line of code that you're trying to put the breakpoint on is like optimized away, like it never happens or any of that kind of stuff, then this won't work. You need to, there's a little bit of finesse that has to happen in C and that kind of stuff. But basically, if you right click here, there's the ability to put a log point. And this is basically a message to log when a breakpoint is hit. And it has some stuff about how things within brackets are interpolated that's actually not true in this using the cortex debug extension for VS Code. This is not quite true, and it's a bit tricky to figure out kind of how it works, but it's basically the syntax for printf. So what we can do here is we can print out, for example, %02x, which basically says print this number as a hex with two, like with maximum of 2 characters. So put a 0 in front if it's just 1 character. So we're going to print these 2 things, and then we need to supply the values of what we're actually going to print. And you don't use commas or anything like that, it's just space separated. So the first thing that's coming in is data at I, and the thing we want to view is CRC. Now the problem is we don't want to view it on this line. We actually want to view it down here like we did in the firmware. But the problem is that there is no line of code here for us to put this against. So it's kind of stupid, but a simple way of doing this is to create a volatile variable. A volatile variable here, which we just increment. So we don't care about this, but we need to make sure that this line of code remains in the build program. So now we can go ahead and put a log point, put the same thing in, and let that run. And what we're going to do is we are going to debug the firmware. So here we are. I'm going to open the debug console. And we're going to see this happen a couple of times. So when we do const setup, it's actually going to run those functions because we build a bunch of packets at that point. So we compute the CRCs. We're not actually interested in this stuff. So let's kind of put some separation in there so we can see where odd data actually begins. And we're just going to skip down. So what you can see is that it's logged out all these values. Just every time we hit that line of code, we log the value to the console. We didn't need to send that message from the firmware. This is all done in the debugger. So it's all done just by getting a breakpoint and then the debugger asking for those values and printing a string. It's really clever, and it's for this kind of stuff, for embedded work, this is such a godsend. You don't actually have to implement an actual printf on the device, which you certainly can, using UART, or using some other tricks like the ITM, which is part of the ARM Cortex stuff, but that's real advanced stuff. We'll get into that one day, I think. That's another thing that I think not many people use or know too much about, but in any case, this is a great technique. So what we can do at this point is we can copy this stuff just into a text file over here, and we'll take a look at to see now what we get on the other side when this actually runs in the firmware updater. So again, we've pre-computed some CRCs as well because we do the same thing as the firmware. So let's just get past that. And in the bootloader now, when we do this right, we should end up with this stuff. So let's copy this stuff as well. So I'm going to come over here and I'm going to just paste this. I'm just going to paste it in line, actually, I think. So we'll just paste it like tabbed over a little bit. So over here. What's going on? Somehow this is 26 lines long. It doesn't really make sense. Okay, so now we got it. The JavaScript stuff didn't pad. So this is actually already telling us a lot about what is going on. This is what we saw in the JavaScript side. So over here, we said that we were sending 9 bytes, right? So the first thing is 9, that gives us a 3F on the output. Then we get the 1, 2, 3, 4, 5, 6, 7, 8, and our FFs. So this is exactly the data we sent, and this is kind of the resulting CRC at each step. If we look at the corresponding thing on the other side, this is not the data that we're trying to send. This is something else completely, right? So what's going on here? This is just not what we're trying to compute. Of course we're getting to a different result because apparently we're putting in different data. Now it'll be really, really clear what went on when I go and show the code, but there's another way of looking at this, and if you ever get into this situation, you can try this technique. If you just take these top 4 items and let's just take those out and put them down here, and then we will put them all on the same line. And if we remember, you know, the difference between big endian and little endian, and the fact that this is a little endian system, we can sort of reverse the order of these bytes and see that that looks a lot like a RAM address. And actually, if you look at the one below it, probably looks like a lot like a RAM address. And yeah, like after that, things get a bit strange. But yeah, that looks like a RAM address. So what's going on there? Well, the problem is that in the comms.c, here we get a pointer to a packet, and we convert that to a uint8 pointer. But here you can see I've made the fatal mistake of taking a pointer to my pointer. So I have a pointer. This is a variable that's on the stack in RAM. And I've tried to take a pointer to that. So that's why we're seeing this address, because that's what we've tried to do. And then, of course, when we go and try to... Sorry, I'm losing my file here. When we go and trying to convert this and do the thing, we're going at that RAM address and looking at the things there. And at that RAM address, we have a pointer. So we actually just have the address of this thing. So that's why this is happening. So the bug is that we need to get rid of that. But I actually used this exact technique to find this problem. And I expected that I had just made some subtle mistake between the two CRCs. This only took me a couple of minutes to find, but I think it really gives a chance to highlight this cool feature. So I hope that made some sense. I hope you enjoyed that. Now that we've actually fixed that, we can try and run this again. So I'm going to run the debugger again. We can take out these log points, which is just the same way that you would take out any other breakpoint. Just delete them. And we can come down here, put a breakpoint there, and let's run our firmware updater. So we're still logging all this stuff on the JavaScript side too, so let's just stop doing that for a minute. Run again. Okay, so now when I actually step through the program, we're going to send this packet. So what you can see is that we received 18 bytes through UART, we built a packet, we stored the packet, and we ACKed. So we sent an ACK message. And then here's our packet. It's 9 things wide, so here's our 9 bits of data, and here's our CRC in decimal. So that's why it doesn't look exactly like what we would do, the 52 we would expect. And we can probably check to make sure that we actually get the ACK here as well. So let's go into the state machine, and we will, when we receive a packet, we'll put a breakpoint down on one of these lines. And I see that something is not quite right because I can't put a breakpoint down. That's okay. Oh, it's because I'm actually not calling comms update. So that means that comms update never actually runs. So let's just run comms update while we're in here. Because I think this is useful to check out. So run the firmware again. Get down to this point. Run the firmware updater. We write the bytes, so we got our packet, then we're doing our system delay, then we can come up to the comms, and I'm going to put a breakpoint down in the CRC part, so when we actually get to this point, which we should hit very quickly. Alright, so now we get to this point. We missed the last one because we had the processor stalled, but at this point we should have our ACK. So this is the CRC that we read, 255. That doesn't look right. I would say something went wrong here. Length is 1. Is anything else right here? The length is 1 and the data is also 1 and then 21. So something not quite right going on here. but this is all part of it. So I seem to have missed something there, but okay. So it didn't match, so we ended up writing a retransmit, and then we're trying to retransmit again and again. But it seems like something is going wrong with our ACK packet. So I'm going to just check the ACK packet. So when we go to create this, let's actually put a before we run this whole program, let's just console.log. I knew we would have some more bugs. Okay, so the ACK packet is 1 with a 15, and then at the end there's 27. So that actually looks about right. That's what I would expect. Alright, let's run this again. Okay, so it definitely seems like something is going wrong with how we are getting this data. So maybe we should actually step through the state machine at each instance instead. I'm going to restart this, restart this. Okay, so we have some data available. Our packet length should be 1, and it is. Alright, then we still have some packets, so now we're going to read data. So we read 21, which is not what I would have expected. 21. Which is hex 25, which is, oh no, not hex 25, but yeah, this is not what I would expect. We do get 255 after that. I mean, of course it can be that the data got corrupted. Let's get to this point when we have all of the data, so we can look inside and see that, yeah, all of that was 255, and then finally the CRC that we receive is 39, the packet CRC, temporary packet.crc. 27, so we actually got the right CRC here as well, but just that first data byte seems to be incorrect. So is that just oh no, 21, 15. So do we have a different value here in the bootloader? Hex 15. No, it's the same. So have I just really missed something here? We actually checked, we went through the CRC, it checked, so this is a single byte packet. It's weird that we end up here. I guess it ends up doing the same thing, so this break goes away. But because it was an ACK, we just went to that point. Okay. So here. So it seems to be the same thing again. we get to the ACK, and we do the same thing again. Okay, so it actually seems to be working. Great. That makes things easier. Okay, so next is going to be checking that if we send a corrupted packet, that we try to that we actually get a retransmit request in response. So let's try that. Bootloader. So now, in order for us to just get a corrupted packet, the easiest thing to do is to just do packet.crc++, right? We add just one to the CRC, and that will now not compute. So if we run this again, and so, okay, so the CRC failed, computed 52, but got 53, so that seems about right. And we, at this point, we would have sent a retransmit. So I think the useful thing to do will be to get to the CRC, and our CRC checks, and is it a single byte packet for a retransmit? Yes, it is, so we're going to retransmit our last packet. Of course, this won't actually help. What we could do is, with our temporary packet, we could just take away one from that, and then that would kind of solve this. So let's do that. Last retransmitted packet .crc, we do set last transmitted packet.crc equals last transmitted packet.crc -1. So okay, so we should have set that now. It says 255. So maybe we don't actually. In this case, we do comms write a retransmit packet. This is asking us to retransmit, but it seems that we didn't write our last retransmitted packet. Is comms write actually doing that? Oh, that's the problem. It's not doing it. Yeah, so great, more bugs. This is excellent actually. So we can do here comms packet copy. And this is going to be copying the source packet, which is going to be the packet that we're trying to transmit, copying that into the last transmitted packet. Okay, let's try this one more time. So we're going to run it. Let's clear that, run it. Get to this point, get to this point. So it's a single byte packet. Our last retransmitted packet does indeed contain what we tried to send, and the CRC part contains 83. I guess the easiest way to do this would be last retransmitted packet. I think we can just do it from here instead. So let's just set this to 82 instead. That's just -1. So then we send that out and we get a packet back, and hopefully the packet this time is an ACK. Yeah, and it is. Great. So that actually works as well. Yeah, and we see it here as well. Great. So the next part of testing is really just checking that we can actually receive a packet on this side. And actually we've done that already. We've actually checked that we can receive a regular packet because we've dealt with packets like retransmit requests, so, and ACKs. So I think what we want to do is to just transmit something that is not one of those. And what we can do is in the bootloader, if we have, if comms packets available, then what we'll do is to get the most recent packet. So we can do a packet read, comms packet, comms read. Then we can just read into well, we can make another temporary packet. This will be our RX packet. We don't even need to initialize it because we're just going to read it this way. We'll read that packet, and then we can do the volatile trick. The volatile x equals 0, x plus plus, and here we can do just a log point, or rather we can just have a breakpoint and see what we have inside that RX packet. I don't even know if we need to do that, right? Because we can just put a breakpoint here when that happens. Okay, so we are going to just send a regular packet from the firmware update code. So we will wait for a packet, and then we will send a packet. So this is going to be, yeah, let's create packet to send. That is going to be packet, new packet, a length of 4, and we will have buffer.from, well, let's do 5, 6, 7, 8. And then we can do UART.write with our packet to send. We should receive that on the other side. Okay. Let's run. And run here. Run. Oh yeah, we need to fix the we need to fix our last transmitted packet. So let's do that quickly. Last transmitted packet. Yeah, maybe we shouldn't send a corrupted packet anymore. That will make life a little bit easier. Okay. Oh, this is interesting. The chunk argument must be of type string or of instance buffer, received an instance of packet. Ah, that's also interesting. Okay, so packet to send dot to buffer. Alright, so we get to comms update, and we can actually run this. So run. Oh, this is interesting. Next write index 0, packet write index 0. If the next write index is equal to the packet read index. How did we get here? This feels like something went wrong. Because I have the feeling that we never actually even get to this point, so the next write index. Huh. Alright, we'll run again. Okay, so the packet write index is 0. And the packet buffer mask, is that computed correctly? Packet buffer length, -1. There are bugs. There are all kinds of bugs here. Yeah, that's good. Now we got a packet. The received packet is of length 9. So that is not what I was expecting. Somehow we received the wrong packet back. This is, Oh, no. This is just stupid. I haven't actually read the packet yet. So now we read the packet. Length 4, 5, 6, 7, 8. Correct checksum. Nothing wrong there. So actually, that is looking really good. And I guess the last thing is receiving a corrupted packet. And for that, we can just do our... Well, we will just check to see if we get a retransmit request. So that's going to be here. So let's put a breakpoint in there. And we can check this nice and easily by doing exactly the same thing, right? Packet to send.crc++, right? We'll just mess up the CRC. Run again. And we should end up in that right place. So here we get our retransmit packet requesting us to retransmit. Excellent. So we're actually, as far as I'm concerned, we've solved a good number of bugs there, and we've solved a lot of the problems that we were hitting. And this is actually a great foundation at this point for us to go on and build a full bootloader firmware update mechanism. I'm confident enough now that we've got the main operations up and running, most of the bugs kinked out, to actually go ahead and do that. So that's kind of what we're going to be looking at in the next few episodes, although there are a few extra things that we're going to need to do as well. So we're going to need to set it up so that we can actually write into Flash. That's a little bit more involved than it seems, and we'll take some time to do that. And likewise, we will also need to take care of the actually writing the client side. And I think we can write the client side and the bootloader kind of independently and try to make sure that they integrate properly together. Right, I think for now we've hit a really good point with this. I'm really happy with this. I'm also happy to, well, for me it's good to show this kind of process, right? I had already noticed one bug in the system, but I didn't realize that there were all of these bugs here. So I like to try to show that kind of thing as much as possible. Like, this is the actual process of going through, trying to figure out what happened and fixing the things that come up. Of course, there are other ways to try to write less bug-prone code, like writing tests. So that's something maybe we'll look at in the future too. I always get comments about that, so it might actually be something. To me, it doesn't seem like watching someone write tests on video would be fun, but who knows? You're watching this, so maybe it is. But yeah, so I'm really happy with the way this has turned out, and I think we can cut it off here. So thanks very much for watching, and I'll see you next time.